Hi, I'm Matt Gaska. I'm an engineer with Siemens in the US working on Cinemeric CNC systems. This is a multi-part course on how to reduce cycle time. Before we get into the meat of the class, we have to go through a big disclaimer. I'm giving you all the example files that I'm working through. Because this class is designed for experienced commissioning engineers, the files that I'm giving you cannot necessarily safely be run on any existing system. There are some potential address conflicts that can occur. And the bad thing about address conflicts is that if you use my code and I happen to be using a variable that something important in your machine is using and I overwrite it, something's going to break and possibly somebody gets hurt. So this is meant to be adapted by folks who are experienced commissioning engineers. It is not for general purpose NC programmers. So in the concept of this course, when we're talking about cycle time reduction, we're talking about mostly communication and program structure related delays. We're not talking about path optimization. We're not talking about how to write a better CAM program. We're not talking about a better post output. We're talking about things that are communication related or structurally in the part programs. There's a lot of use cases for this because there are a lot of machines you just go and you put the tool in and you just cut and cut and cut and cut. Those type of machines aren't going to see a whole lot of benefit from the techniques in this. This is for the machines where you have a lot of handshaking between the NC and the PLC, or you have a lot of motion that needs to be parallelized, or you have things that you're loading a lot of variables and you need to load them faster. So this is more for the machines where we start caring about, hey, if we can knock out 30 milliseconds here, 30 milliseconds there, 100 milliseconds here, that's the kind of thing that we're looking for. In the notes that'll be below the video that you're watching, there will be a link to a Google Drive, and that will have all the source material that I've used for this course. So any of the programs that I'm running, I'd like you to go get them and open them up and follow along with me. One of the things that's going to be a little bit weird is that in every slide I'm going to have them numbered with a 3-digit code because I made my samples in the order that seemed to make sense. And then when I started teaching this class, I found out that the order I had made them in was really awful. And so they've all been redone. But because so many of the screenshots already have that ID number in them, they don't go in order. So just watch out for that. So because we're going to be doing a lot of comparison testing and it's about time, I want to show you the main timing configuration that I'm going to use. This variable $AC operating time, it's a system variable, and it's enabled by turning on machine data 27860 bit 0. And the way that we use it in a part program is we set it to 0 to initialize it, and then we can read it out however we want. Typically, I'm going to do that in a message, just throw it to the header. You could store it in variables if you're doing some kind of your own testing. It's a very useful variable in many, many use cases. The system that I'm using, I have an EPO time of 6 milliseconds. And for reasons that we'll explain in a whole bunch of slides later, the minimum duration that I can record with this function is 18 milliseconds. Another piece of useful overhead that I have in a lot of these programs is I use R0 just as an interpolator tick counter so that I can trace it. And that way, when I'm doing my traces, I have something that shows me each interpolator tick, and I don't have to use cursors because I'm really lazy. And I'd rather write code than count because I failed Sesame Street. And just as long as we're on the slide, again, I've got a 6 millisecond interpolator clock. PLC scan time in my case is about 20 milliseconds. 20 millisecond PLC scan time is on the fairly quick side for 840D solution line. 50 milliseconds would be considered a very slow one for 840D solution line. And for Cinemeric 1, PLC scan times of 5 to 8 milliseconds would be considered pretty dang quick. Slower would be about 20. I chose to do this on a slower PLC cycle time because it makes a few of the things a little bit more dramatic. So it's easier to visualize, therefore easier to point out and explain. So let's look at the code that I use for R0 to show you the counter. So this is going to show up in a lot of programs kind of as a header. Again, make sure R0 isn't something important. Make sure sync action ID 1 isn't doing anything important. That's up to you guys to figure out. You're commissioning engineers, you do this. So we initialize counter. StopRe, start my sync action. So I just keep adding 1 to R0 constantly, every tick. Then run my timer again and show you how many ticks it took. I use the same trace configuration over and over again, so I'm not going to explain it for each test. All the sample programs are going to use the variable $AN SL trace equals 1 and 2 as start and stop triggers. I'll show you the sample code of this. R0, which is my EPO tick counter, will always be my first trace. It'll be yellow. R1, which will be something that I'm manipulating as needed per test, will be the second trace. It'll be green. Path velocity will obviously be the third trace. It's cyan. And sometimes I'll put in a fourth trace as an axis position, red. So you can see over on the right side of this slide what my triggers look like when they're set up. If we look at the code that I prepared for this just as a sample, I initialize the trace trigger, initialize my EPO tick counter, set up my operating time. Again, this is going to be common overhead for all these because I'm working off of this structure and just modifying things. I start the trace and I reset the trigger. The reason that I reset it immediately is that way when I screw something up, instead of triggering on trace equal 1, by doing this, I immediately set it back to 0 and I don't get a false trigger and have to start and stop a trace again and irritate myself and start cussing. So trigger it here so the trace starts. We dwell for 100 milliseconds, stop the trace, and then I'm going to display the elapsed time. So this is more of what the whole overhead looks like. So if we look at the trace, we've got about 200 milliseconds of total time taken up. There's some things in here that have delays that I haven't explained what they are or why they exist. Even though we only dwelled for 100 milliseconds, we get to see my R0 as my yellow line, counting up 1, 2, 3, 4, 5, 6, 7, however that goes as we're going. And again, we're just using that so I don't have to cursor and count to figure out where EPO ticks are. One of the things that we're going to spend a lot of time doing is avoiding unnecessary StopRe statements. Again, this class is for experienced commissioning engineers. You guys know how StopRe is used to suspend read ahead. If you need some really detailed information on it, I've got another video up on YouTube if you want to get down to the weeds with it. But the reason that they're bad is they do two things. One, every time you call a StopRe, you suspend execution for 3 interpolator cycles. So in my case, 6 millisecond depot time, which is pretty common, pretty reasonable. That means it's 18 milliseconds every time you call one of them. You also have to drop your path velocity to 0 when you call one. That's one of the side effects of it because everything has to stop. All the data in all of our variables are fresh. Now we're going to carry on. But that has 2 negative effects. So we want to avoid those whenever we have to. If you need them, you need them. You have to have them in there sometimes. Sometimes they're absolutely without question required. But we're going to be trying to minimize them. So I'll give you the information for the whole other video I recorded as a PDF as part of your download. You already have it in the 006 file, and the link should also be available to you. So this is a slide and set of programs that's fairly detailed, and the purpose of it is that I need to prove to you that yes, these things actually do take up time, and it is real, and some guy on the internet isn't just making things up. So came up with sample programs and traces. You have them all. They're in the download package you get. So we're going to talk about this first program called Clean Sample, and let's take a look at it. What's different than normal is I created an array called time, just for the purpose of saving times, and a counter. Everything else is the same thing we've been seeing. Set up the trace triggers, get R0 counting per tick, so on. So I start my trace, and then I manually increment R1 6 or 8 times or whatever that is. Remember, I failed Sesame Street. I was always afraid Big Bird was going to back my eyes out. But however many times that was, we'll see that in the trace. And then we dwell a second. And then I initialize my timer. Run through a loop 10 times, incrementing R1. Save the value of my timer. Run through another loop 50 times, incrementing R1 again. Save the time again. The reason I'm doing it this way is because that way it gives me I know time 0 is before I entered the loop, Time 0 is when I'm here. Time 1 is the second execution time, so it's the total. It's not a delta. There's some reasons I did this that make sense in my head, but means we have to do a little bit of math. So let's take a look at the trace that comes with this. So if we look at it, we've got R0 that's just continuously incrementing, and it looks nice and smooth because it's fairly long duration, and all these stair steps are smoothed out just by graphics. We ran out of pixels. Here's where I incremented R1 6 or 8 times, whatever it was. Here's my 10 increment loop. Here's my 50 increment loop. Because all of the R1 variables are processed in look ahead, they all get done in a single epo tick. And we're going to look at a zoomed in view of this chunk right here to further demonstrate this. So R0, our yellow line, we see the stair step that each one of these stair steps is 6 milliseconds, 1 epo tick. We can see that, yes, all of them did get done in 1 tick. Now we're going to hop on over and we're going to look at the StopRe sample. What I've done differently here is that anytime I go to increment R1, I have a StopRe between each increment. So the handful of times that I did manually threw in StopRes, and then in each loop, threw in a StopRe, threw in a StopRe. Let's look at the trace. I'm going to prove this to you 2 different ways, both with math and with trace. So we look at the trace, and R0, again, is our single epo tick. This is the early chunk of the program where I'm manually incrementing R1. So we see R1 go 0, 1, 2, 3, 1 at a time. And we can also go 1, 2, 3 epo ticks, 1, 2, 3 epo ticks, 1, 2, 3 epo ticks. This is what I'm using R0 for. We also see our timers up top. We go back and look at the document. Timers are 198 and 1.116 for 10 and 50 loops. If I do the 50 loop calculation, if I take my 116 minus my 198 where I started, subtract off that minimum time of 18 milliseconds, divide by 50, divide by our epo time of 6 milliseconds, I get exactly 3. So yes, it really is 3 epo ticks for every one of these. Now we're going to look at StopRe's sibling, NewComp. If you're not familiar with NewComp, it's the programmatic equivalent of the setMD active button. So any of the machine data that need a setMD active press, this is a way you can change those machine data in a part program and then activate them immediately. NewComp is going to be an 8 epo tick delay. So I've taken the same program we had for StopRe and just replaced all the StopRes that were relevant with NewComps. So increment manually, put it in my loop. Let's look at the screenshot of the trace. So we've got R1 incrementing by 1. And then I've got my R0, my counter. We've got 8 and 8 and 8. We've got our timers up here. Look at the document. I'll do the same math. Off those timers comes out to exactly 8 interpolator ticks. So these things can be super useful, but they need to be used very sparingly. Otherwise, you just start building in delays. Like there are some systems out there that have a very, very heavy prog event file that does some hefty kinematic work, shuffling around kinematic data, that have a pile of NewComps to the point where when you hit cycle start or reset, you as the operator will notice a delay. So you have to be careful with these. Use them sparingly, but if you need them, they're perfect. So we've talked about regular StopRes. Now we're going to talk about implicit StopRes. The reason that we have what are called implicit StopRes are there are some variables where we know that we can never process this data in look ahead because it's just going to be inherently useless. For example, if I want to read an axis position in a part program, if I read the variable for where is my axis, if I read that at the time of pre-processing, that's completely and totally useless because we may have 500 blocks worth of code between where we pre-process it and when we actually get there. So the axis is totally moved. That data is junk. We have to have a StopRe there to stop pre-processing, wait for execution to catch up to look ahead, for them to be together. And so we've got some of the variables that have this implicit StopRe built in, meaning that whenever you call one of these variables, it's going to have the same effect as calling a StopRe, so you don't have to. If you look over on the right-hand side, there's a list of variables that are done in pre-processing, anything with the prefix $M, $S, so on. Those are handled completely in pre-processing. Anytime you read or write one of them, pre-processing. Variables with an implicit StopRe, anything with the $A prefix, so like all your axial data, all your $AC data, like for your measurement stuff. That timer function we keep using, the $AC operating time, includes an implicit StopRe. $V is servo data, and if we put a $sign in front of a R parameter, it'll include the StopRe. If you don't have the $sign, it's done in pre-processing. So that one's a little unique. So just to demonstrate this, I've got two-part programs that are the same as what we did in example 4. One of them is actually the same verbatim, where I just run through 10 loops of having a StopRe in there, and I give you the timers. We look at these programs. The only thing that I've done different is I took out my StopRe, and I made up another timer array that's junk, whatever, and I read in $AC operating time. Both these programs run in exactly the same amount of time every time. This should also be pointing out why, if you remember, I keep saying I have an 18 millisecond minimum time using this operating time function, because that's the time between one StopRe to the next. So that should be kind of sticking out right here as well, which is why I picked that variable instead of an axis position. Sample 3 is to demonstrate that when you have a series of variables that you have to read that include implicit StopRes, if you bundle them up in certain ways or change the structure of your syntax a little bit, you can execute much more quickly, get the same thing done, and not have so many implicit StopRes slowing you down. So let's take a look at the code. So sample 3 is some completely and totally useless code that no one would ever write, but I'm going to use it to demonstrate the concept of how we can eliminate some of these implicit StopRes while still accomplishing the same task. So the first loop that I run through, well, it's not a loop, I just do 5 reads of x-axis position and throw it into an array. Cool. That takes 108 milliseconds, because each time I hit the $A variable, I get an implicit StopRe that's 18 milliseconds each time, plus the time for your $AC operating time variables and so on. It adds up, which not so awesome when you're trying to go faster. What I do in the next example is, instead of putting each read on its own block, all of my reads are on one block. Yeah, there's some word wrap going on here. This is one block. So this is done in 36 milliseconds, which means we've got that 18 millisecond per StopRe. So we've got the one for my timer. We've got the one for my one-line read. We cannot get any faster than this. This is as fast as we're going to get if we have to touch those implicit StopRe variables. So instead of having 5 implicit StopRes for my axis position reads, I only have 1. It's awesome. Yeah, it's still stopping everything, but it has to. We don't have a choice about that, but we've eliminated 4 of them. Now, let's say that I want to do something with those positions that I've just read. Like I have to take those variables and do some math, calculate a work offset from them, calculate a, I don't know, whatever. You got to do a something with the thing. Because they're now in local variables and stored, when I manipulate my local variables, that's all done in pre-processing, and we've got our minimum test time of 18 milliseconds, which is awesome. That's the best we're going to get, which means that combining the second blob and this third blob is a very, very efficient way to go. You take your data that has the implicit StopRes, you bundle all that into one line, which, yeah, it looks a little bit ugly. It's not so much fun to read, but it's fast. Then once you have it stored, then you can operate on it freely without getting the time penalty. Sample 4 is going to be an example of if you have something from the PLC that you have to read and you need to do a series of big if statements where you have a lot of choices to be made, it's how to do this quickly and efficiently. So this is very commonly done like with A subs, where you read a $A DBB variable to decide which branch to go down. So first thing we do is, let's say $A DBB is what's driving which branch we choose in this program. I'm going to read that up in the header, one of the first things I do, and I'm going to shove that into a local variable. I don't need an explicit StopRe because I start with $A. Awesome. Now after this, I don't have any more implicit or explicit StopRe statements because I'm working on a local variable. I'm just reading what is event selector. This is all process and read ahead. Yeah, you're probably going to have actual motion and real things in here that are going to cause other goofy things, but this structure only has the one implicit StopRe and no other delays, which is pretty good. So 2 quick closing thoughts on the implicit StopRe topic. First, we should now understand, and it should be obvious, why we have that 18 millisecond minimum time when I use that $AC operating time. It's because it includes an implicit StopRe. We're getting the time off of that. That's where it comes from. The second thing is that if you have something that's power line below 7.4, the implicit StopRes were kind of hit and miss of which variables had them and which didn't. Even like just saying like all $A variables have an implicit StopRe. That was not true prior to Software 7.4 and Powerline. Software 7.4 and Powerline is somewhere around 2006, 2007 vintage. So there are going to still be a lot of machines out there where this doesn't work as I'm showing you because it wasn't documented, it wasn't described, it wasn't published. It kind of sort of worked for some things. If you're planning on it working, you have to do it on your own. You have to do your own testing to make sure how things are going to behave. You have all the test programs that I'm giving you. You can put in your variable and see what the timers do. So we're going to talk about M codes. The deal is that when you fire off an M code, that's a signal from the NC to the PLC, and the PLC has to have time to respond. So what happens is when you fire an M code, the NC is going to drop your path velocity to 0 because that M code may be doing something that says, hey, we're going to do a read and disable, we're going to do something, like we're going to wait for a tool change door to open. So inherently, the NC says, I need to stop all motion before that event happens so that we're not moving when we try to open the door, which is a good thing for not crashing. It's a bad thing for being slow. So you fire off an M code, your path velocity is going to drop to 0, and the NC program is going to suspend for 1 PLC scan cycle. The reason it suspends like that is it gives you 1 scan cycle to set your read and disable. So for example, again, if you're opening a tool change door, you have a chance to get that door open before you move the machine into it, and then there's no crashing. And no crashing is a good thing. Unlike our StopRes, though, a M code does not suspend look ahead. So everything that's going on in look ahead keeps flowing right on by while the M code is being executed. There's a sibling called quick M codes, which use the QU syntax. And the purpose of these is that they have pretty much the same behavior as a regular M code, but they don't have the 1 PLC scan program suspension. So they do run a little bit quicker, but in reality, you're dropping your path velocity to 0 when you fire one of these off anyway, so that's going to be more of your time hit is the ACK and deck phase of it, but they are quicker. Cases where I'll use these is sometimes I'll use quick M codes to say, open a tool change door while I'm going to start moving, and I'll get moving and I won't worry about if you're open or not, I'll go check it later. Or maybe if I have something that doesn't have feedback, like coolant for a spindle, I don't need that time to have the possibility to set a read and disable because I'm not going to set one anyway. So they can be useful and they can save some time, but we're talking about single PLC scan cycles, which add up eventually. One of the things I like to do is create pairs of M codes that have the same function, but the difference being that one of them will have a read and disable, one won't. The way I like to do this is I like to do something like add a prefix to them. So if M60 means open my tool change door, M1060 means open the tool change door without read and disable, which makes it easier for me to keep these things straight in my mind because I know by adding 1000 means no read and disable. And the use cases I have for this are when I want to get many, many things moving together at the same time. I don't care if things are done while these things need to start moving. They just all need to get up and go. They all need to get up and go together, and then we'll check later to see, have you actually finished? So an example of this is I'll fire off a quick M code of M1060, which means just open the door. While that door is opening, I'm moving over to some kind of approach position that's going to get me pretty close there, but not actually running through it. I'll fire off an M60, which will have the read and disable. So at this point, if I'm still moving, I'm going to suspend on this line. If I've already gotten to my safety approach position, whatever we call it, that's outside the door, then this blips by just as fast as firing one M code, and then I can go in, approach my tool changer, and do all that. I use this in many, many cases all over the place as a programming trick, and it works very, very well, but you have to be careful with it, which is why I like having very, very clear definitions of which is the one without the read and disable. I also like to keep those up in high number ranges because most operators think that M codes stop at 99. They're not going to punch in an M1060 by accident. Well, they might, but hopefully not. Hopefully you get lucky. Now, one of the things you might be thinking is, what happens if I put an M code on the same block as motion? The default behavior is based on machine data 22200 set to 0. And what will happen is that before the motion is executed, the M code will be issued. That is the default behavior as configured by that machine data. Now, we haven't heard me doing a whole lot of disclaimers throughout these videos because I put the big one in front that says, yes, this is for experienced commissioning engineers only, so on. This is one of those cases where you can do a lot of damage very, very quickly if you do not understand everything that's going on under the hood related to the machine-specific implementation of how they've done PLC, how they've written tool change cycles, how they've written a lot of code like that. This is one of the big scary ones. So, big disclaimer right here. If you don't understand exactly everything that's happening in the background, don't try this at home, kids. So now if we take this machine data and set it to a 1, what this does is it changes the behavior of our M codes so that when we have motion and an M code together on a single block, it will issue the M code in parallel with the motion, which is awesome if you have decent length moves. If you have super, super short moves where time of motion is similar to the amount of time it takes to issue an M code, it gets a little jittery and a little wonky. But the nice thing is, if you have long blocks like open my tool change door while I'm going to be coming over there anyway, you can put both those on the same block and get a nice fluid, smooth motion because the M codes don't cause any kind of read and disable, and they don't wait for that PLC acknowledgement before issuing the motion command, so everything moves in parallel. Well, if you want to make it even faster and have shorter blocks, you can also tie this together with a quick M code. So let's take a look at a program and let's look at some traces. So the program's pretty simple. All I'm doing is I'm starting at X0, going X10, going X20, returning it home to 0. In the next example, I throw an M60 in the middle of it to see it break up path velocity. I do the same thing by combining motion, the X20 command, with the M60 on the next one. And then I try it as a quick M code. So let's take a look at what the traces look like. So the left-hand picture is when I have the machine data set to 0, where I'm issuing the M code before the block motion starts. Right-hand side is where I've set the machine data so that the M code can be issued in parallel with block motion. Can't do this in a program because it requires a reboot, so I just did it 2 times separately. So we look at the first motion, and that's no M code, and everything just moves along. Path velocity is cyan, position is magenta. I throw an M code in between my X10 and X20 blocks, and wouldn't you know it, comes to a nice hard stop. I try it putting the M60 on the same block as the motion for X20, comes to a stop just the same way. Try a quick M code between the 2 motion commands, comes to a stop. Try a quick M code on the motion block, comes to a stop. So this is all exactly as expected. Let's look at the right-hand side where things are going to behave exactly as expected, but this time they'll be faster and less boring. One of the things I forgot to say earlier is that these numbers on top here are the execution times for each chunk of motion. So it's substantially faster when we keep things moving, which is unsurprising. So I set that machine data to 1 so we can issue the M codes in parallel with the motion. And if we just put the M60 in the middle of them, we get the exact same time as if this machine data was set to 0. Now here's the interesting one where I put the M60 on the same block with X20. We get a substantial reduction in time. We don't drop our path velocity. We can see it here. We don't see the stop in the position, and it just rides on through exactly like we're wanting here. Again, if I put the quick M code in the middle, yeah, it's a little bit quicker, same as in the first case, but not substantially. It basically gets me 1 PLC scan, which, okay, that's something, but we still had to stop. If I put the quick M code on the same block as motion, I'll get the same execution time as this step. So do I really need a quick M code? No. Is it good practice in case it's a really short block? Yeah, it can help, but it's not really required. So like all M codes, M17 gets sent down to the PLC and requires a 1 PLC scan acknowledgement because it's an M code and they all require it. That's fine. The challenge being that, like all M codes, it means it also drops your path velocity to 0. Now, when you're ending subroutines, why do we need that delay? How does that help us in any way, shape, or form? It doesn't. So for all practical purposes, I no longer use M17 ever. I just use the ret command for return, because ret is processed in the look ahead. It doesn't mess with your path velocity. It doesn't take the one PLC scan cycle acknowledgement. So it's faster, smoother, better. Everything's a winner. If we look at the little sample program I wrote, all I did was do a simple move from X0 to X10, call the sub that ends in M17, X20. Same thing for return, ret. Go from X0 to X10, call a sub that ends in ret, come back to X20. We can see that the M17 causes our path velocity to drop to 0. Ret does not. It's a very simple, quick fix that improves a lot of subroutines. There is a machine data to make M17 behave like ret, but there's a bunch of reasons I don't use it. One, I can't remember what it is, and it takes me a while to find it. Two, it doesn't exist back to the beginning of time, or the 90s anyway. Therefore, I would have to pay attention to when can I use it and when can't I, and I'd have to, remember things. And that sounds like something that I don't care enough to remember. It's just easier to use ret everywhere. And it's just so dang easy just to use ret as blind copy or find replace. And yeah. All right. One of the things that can be challenging is having to update variables at specific points in a part program. The challenge is that normally they're going to get done in pre-processing, so you have to throw StopRe, which breaks up path motion and delays you and all the other bad things that go along with StopRes. One of the tricks that we can do is use a when true do statement. So doing my standard little example, I'm going from X0 to X10 to X20, and I want to increment R1 once in the middle of this block. Using this when true do statement is going to, remember sync action conditions, when is the one shot. This is going to increment R1 once. Beautiful, exactly what I want it to do. If I just do a do statement, what'll end up happening is it'll fire up the sync action, and it will keep running through the completion of the next block. So instead of incrementing once, it's going to increment a couple hundred times. So let's look at the slide and the trace. So if we look at, I did actually have 4 of these tests in there, but let's look at the first ones for R1. So here's when I did my when true do, right in the middle there. No interruption in path velocity. Position looks smooth. I get incremented once. If I omit the when true do and just do do, I increment, what does it look like, about 20 times or so. Again, no interruption in path velocity, so it's smooth motion, but we incremented way too many times. Alternatively, for the red line, I put in $AC param, which we know is anything $A breaks up look ahead has the implicit StopRe. We can see that using that doesn't make a difference compared to using the R parameter. So it works for all kinds of variables. And this is a pretty powerful function. This is a pretty special case example, but we're going to talk about the pause and pause commands. What these are used for is, especially for auxiliary axes, where you just have to get things moving and you'll worry about how they move together later. It's not really a good coordinated motion like you would have with a axes in a part program. It's more about, let's get multiple axes moving at the same time without really being tightly coupled like a regular path. So we're going to look at the code here. So again, this is going to be for axes that have to move somewhat uncoupled, like you're trying to get a whole bunch of them ready for a tool change that are all moving out in free space. If you have fancy end effectors with many axes on the head and they just all have to retract at the same time to some known location, we'll worry about when they get there together later. That's the kind of function we're looking at. So the first example we're going to look at is going to be pause for positioning a synchronous command. So I'm going to send my x-axis to 100 millimeters at a feed rate of 5 meters a minute. So when this line hits, X is just going to take off and is going to go to X100. We're immediately going to go to the next block because this block will execute immediately. It's not going to stop and wait for that x-axis command to finish. And we're going to go to Y30 at 500 millimeter per minute. Now they're both going to finish their commands. We're going to get here to this dwell block, the G4 F2. We're going to get here when Y hits 30. X may or may not be at 100 at this point. We don't know. So the reason that there's a long dwell in here is I'm trying to give it some time for X to get there, so I'm sure that it gets there. Which means this is kind of a silly thing, but if you know you have moves that are, like distance ratios or time ratios of like 10 to 1, because this is moving around like an end effector or something that's really well known of what your motions are, maybe this is the right thing. Let's look at the trace real quick. So if we look at the trace, change colors. R1 I'm now using just to help keep track of which sample I'm on. My X position has become magenta. My Y position has become cyan. So we can see in this example, Y reaches its position here at about 1.8 seconds, give or take. X doesn't get to its position until about 2.4 seconds, give or take. So when I said, we went on when we got to Y30, well, I meant it. So if we tried moving X after this, we'd have some weird things that happen. It's a special use case thing, not common. The next thing I'm going to show you is basically the same thing, but I'm going to replace that long dwell with the wait P command. Wait P means wait for positioning axis. So we go to Y30, and again, X may or may not have reached its final position. Wait P means sit here and wait until that asynchronous positioning axis finishes its motion. Then carry on and go to Y60. Okay, let's look at the trace. Y goes to 30, stops, waits, because X is still moving. Once X finishes, Y resumes. So this can be a more definitive way of coupling these axes up. We got them all moving, we got them all retracting together, but this gives us a little bit more concrete, yes, we know that X finished where it was before we started doing the next thing with Y. This next example is much more realistic, and I use variations of this quite often. This particular sample is pretty silly because not that the syntax is silly, but that the conditions that I chose are just really dumb. Normally I would have a much more complex and meaningful condition. I use this a lot with end effectors where I have to make sure that multiple things are retracted before I can start moving a slide carrying several end effectors sideways. Like I don't want to break off the pieces that are hanging down while I start going sideways. But yeah, this example is, as written, is really silly because this is just a really awful condition for that to be the only thing. But what I'm going to do with this is I'm going to say, once we've completed some things that says we've got enough pieces retracted to move X, go ahead and start moving X. That's the purpose of this, is that we're going to wait for my Y-axis position to get above 20 millimeter, and then we're going to tell X to move as a sync action to 50 at its feed rate. So what I do is I fire that up, so that's going to sit there running in the background like a sync action does, just sitting there evaluating condition. Start Y moving. And then just as a belt and suspenders thing, I'm going to throw the wait P command in here again. I don't know when these axes are going to finish. That way I'm sure X is done before I dwell and return to 0. So let's look at the trace. Looking at the trace. So X and Y are both stopped. Y starts taking off. Y hits 20 millimeters here. X starts taking off. And then they both move and they get to the end at some point. Actually, it looks like they get to the end pretty close together, and we're just lucky about that one. Now, what you'll notice is we have this little hiccup here in the Y-axis position. Because what's happening is with this command as written, this hiccup is caused because it's treating the X needs to accelerate here. It's treating this like we're making a corner, like it's a coordinated move. So Y has to throttle down its velocity so that X can speed up and they can make a corner together. That's usually not what I'm going for with this. Usually that's not such great behavior, but depending on what I'm doing, this may or may not be the right thing to do. I've used it before. I'm sure I'll use it again. And I've saved my favorite one for the last. So what I'm going to do here is I'm going to use the original pause command like we had in the beginning, but I'm going to use a sync action with it. So what I'm going to do is I'm going to fire up a sync action that has my same garbage condition of y less than 20. Note that it's y less than 20, then greater than 20 this time. I'm going to say crank the feed pot on X down to 0. This feed pot, the override value, this is multiplied with the feed pot value that comes back from the PLC. So it's an independent one that we can write to cyclically in sync actions. The way I've written this condition is that I don't have to set it back to 100 because as soon as I stop writing it, it goes back to 100 on its own. So I saved myself another chunk of code there. So what I do is crank the feed pot to 0, Command X to start, using the pause A command, get Y up and moving, and then as Y is moving, we'll go past Y20, the feed pot will release, X will take off. Wait P like we always do. It's like the trace. So they're both sitting here stopped. Y takes off, hits 20, X takes off, does its thing, and then no hiccup, no glitches, just beautiful smooth. This is a personal favorite of mine that I use often. It's a little tricky. It's a little kind of sleight of hand going on of, yeah, we're just going to start telling Axis to start moving, but we turned the feed pot down to 0, and we're just going to hold that at 0 until it's clear. But I use this one a lot. Now, when we're using these commands, very often we're going to be combining them with M codes without read and disable, just to get things moving. And again, this can be things like when we have to go to a tool changer. We know we're going to have to do several things. We're going to have to open doors. We're going to have to do this. We're going to have to do that. How can we do more things in parallel? And this is something that you as a builder have to know. It's your machine, it's your mechanics. Same thing with complex end effectors. There's a lot of times where we just need to get things moving, and we'll be resetting our end effector between different points on part. Like we'll be doing all this reset and retract stuff while we're moving between holes. That's very, very common. Again, this is for the machines where that extra 30 milliseconds somewhere means something. When we're looking at optimizing the interpolator cycle, the thing that we need to think about first is what is more important to this system that's going to make the whole thing run faster. Are we going to be doing a lot of things like I've been showing in this class where we're reading variables that have a lot of implicit StopRes, where we're doing a lot of handshaking, where we're doing a lot of communication? Or do we have something where we have a lot of sync actions that need to run at a particularly quick clip for some reason? That's one way of looking at it. The other way is if you have a lot of part geometry where you need a lot of CPU resources dedicated to look ahead to smooth out a big CAM program that you've put in, that's going to be a totally different answer. Now, I've just made up all these numbers kind of based on roundiness. We're just going to pretend that typical servo cycle. Servo cycle is how often the NC and the drives communicate. Typical setting for that is every 2 milliseconds. There's a whole bunch of fine interpolators involved and so on, but that's a different discussion. We're just going to pretend that it takes a whole servo cycle for the NC to do what we're just going to call overhead. Overhead would mean things like reading the axis positions in, running the control loops, like the closed control loops, sending out new commands, any of those like $a DBB variables where we're communicating with the PLC, that kind of stuff. We're just going to call that the blob of overhead. And that's going to be a fixed amount that really isn't going to change depending on what we're doing with the machine. We're just going to call that fixed. And just to make my drawing easier, I made that take up one whole servo cycle. So now, if you look at the drawing, let's say I've got an EPO multiplier of 3, which would be 6 millisecond EPO clock. That means I have 2 servo cycles left to do things like part program processing and to run my look ahead and to do more time execution for more sync actions. Lots of these kinds of things. If you run into the case where you're doing very, very simple motions and you're just trying to do things fast, Maybe you can even take one more tick off of that. I don't know. But for example, if you have big flowy programs, like you have big 5-axis contours, and you're doing mold and die parts, the opposite can be true. Because processing a large complex program in look-ahead is CPU intensive. One of the things that we'll often do so that the machine will actually run smoother, we'll slow down the interpolator by an extra servo cycle. Because what that does is it gets me an extra servo cycle to do look ahead for every interpolator tick. And while this sounds counterintuitive, it means that we can read in more program per interpolator tick because we're doing less overhead work, which means we have more CPU resources available to do look ahead. So we look at my drawing with the yellow and the blue. You'll note that my top one, where I've got the EPO multiplier set at 3, so 6 milliseconds, I've got 8 yellow blocks for program processing. Look at the bottom one, where I slowed it down by 1 tick, got an EPO multiplier of 4. I did 1 less overhead cycle, and so I got that overhead cycle back to do program processing. Both are completely and totally correct, but you have to decide which one are you turning the knobs for. Both do work. Both work beautifully, but you have to pick one. There has been a large change when we went to Cinemeric 1 from 840D power line and solution line related to how the PLC works. In 840D power line and solution line, we had a hardware PLC. So to get a faster PLC, you had to get different hardware and get a different PLC in it. Like we had S7 314s, and we had S7 317s, we had S7 319s, so on and so on and so on. Different generations of NCU had different hardware in them, and that's what you were tied to. Cinemeric 1 is using a soft PLC. What this means is as you get a higher performance NCU, the scan time of the PLC also increases. I'm putting the slide in because Cinemeric 1 is quite new at the time of this recording. Not a lot of folks are aware of this yet. So this is a quick slide showing some relative performance that was put out by product management. Point being, your PLC scan time is now impacted by your NCU selection. This one's a little bit off topic, but related to our friend StopRe. There are a lot of cases where we're going to have to load very, very large quantities of data. For example, if we are loading multiple conf tables for the machine at once, if we're doing big curve tables, if we're loading huge arrays of data that's going to be used for some kind of complex process. One of the things that will happen is that if you have excessively large programs without any motion, you're going to start getting faults that say reorg not possible, which effectively means that look ahead lost track of the last corner it had made with actual motion, and it's not seeing another motion coming up, which is important for some internal things. And it's not really relevant or a problem when you're doing this, but people don't like to see faults. So traditionally what we'll do is if we are doing some kind of long data loader, your mileage may vary. It's going to depend on how you have your look ahead set up, but typically every 200 blocks or so, we just toss in a StopRe and the reorg alarm goes away. All right, in the intro I said I wasn't really going to talk about servo optimization or programming stuff, but I kind of lied a little bit. A couple things that I'm going to point out of things that you can bring to whoever your expert for servo optimization is. There's a couple of commands that are kind of unique that we use in special cases. First off, one of the things that we should all be aware of is that more often than not, the motors are oversized in terms of torque available compared to what the mechanics can handle. This is done for a couple of reasons, including inertia matching and safety factors when doing motor sizing. So it is extremely common that if you run motors at torque limits, they're going to break and snap something. I don't know what, but of course it's going to be the most expensive, longest lead time part because that is how the universe works. That being said, drive parameters 1520 to 1523 can be used to set a torque limit at the drive so that if you have a component where you know what the torque limit is that it'll handle before it snaps, go ahead and set that limit so we don't break anything. One of the machine data that we use is the jerk factor for G0, 32435. What this does is it takes the programmable dynamics value for dyne norm and we'll multiply it by what I usually enter in 3 or 4 when you're in G0, which means that, hey, we're in G0, we're off part, let it just rip, let it bounce. There's some practical limits to this, but it's usually a good thing to set. Another couple settings worth knowing about are the G0 tolerances. The purpose of these is that when you're in G0, that automatically means you're off part. Why not let the control take a little bit rounder of a corner, let it clip it a little bit more, let it do it automatically. As soon as you are off part with G0, you're going to get a faster program execution, especially when you're doing things like drilling hole to hole, automotive, aerospace, or you're going for a tool change. These things are very beneficial. If you're on part, G645 is kind of considered a minimum for everything. G646 for turning has proven very effective. Cycle 832 for milling is also extremely effective. If these are new terms to you, please contact your servo expert. Make sure something like them is being used. If you're off part, there's a couple commands that are not used very frequently because they are extremely aggressive. 643 and 644 are in the same group as 645. And what these are corner rounding techniques that basically are saying, when we go around that corner, yeah, jump the curb, knock over the fire hydrant, drive through the fence, everything. They are extremely aggressive corner rounding methods, but they're extremely fast. If you look in the book will tell you that these are not released outside the tool change zone, which is a horrible translation. And what it means in English is don't use it on part. You're going to clip a corner. Don't try it. Brisk and drive are in the same group as soft. Brisk means no jerk limitation, so that's already pretty dang aggressive. Drive means we're going to be able to accelerate at current limit. So if you haven't set current limits well in 1520 and that group for the drives, you're probably going to break something. These are aggressive commands, and they are very fast. Something that may be beneficial for your servo optimization expert is the use of either jerk adaptation or OJET. Both these are very similar functions, minor differences, about a 1.5 difference between them in price, a little bit different capabilities. It's going to take an expert probably a day or two to sort out which one's the right one to use. We have a function called the jerk filter, which controls how we send commands to an axis. It basically smooths commands before it gets to the closed loop component. The downside of smoothing commands is that it also can take some of the aggressive edges out of the command and make the axis a little bit slower, which, when we're talking about running things faster, is obviously a bad thing. These pair of functions both have the ability to automatically switch between different sets of jerk filters in G1 and G0 moves. They can be beneficial in the right case, especially very large machines where you have very large jerk filters like 100 millisecond or better. They're worth investigating if you really care about small amounts of time. There's another function called comp path that is pretty new. Comp path, what it does is it's ideally for when you're doing a lot of hole-to-hole operations, like either putting a lot of holes into aerostructures or putting a lot of holes into an automotive part. What it does is it has the ability to do some fairly aggressive but well-planned corner rounding in the G1 to G0 transition. It works pretty well in some cases. If this is part of your market, it's worth investigating. It's not a solution everywhere, but it can have some good effects when used correctly.